This workshop that we're going to have today is an optional workshop for the course. The course has not started yet. And one of the reasons we actually have this workshop is for you to learn about the course, that if you didn't know, that we have this course, and this course is free, and it starts in 1 month roughly, even less, I think. So yeah, we don't have a lot of time to actually, we're still working on preparing the content, but I will also share the link here if you haven't signed up. And what I want to ask you to do is give this video a like, so YouTube starts recommending it and more people will learn about the course and about this content. So please take a few seconds to hit this like button. And in the meantime, I'll talk a bit about the course. So in the course, we will implement a RAG system. RAG stands for retrieval augmented generation, right? Which is about creating a system that allows you to speak sort of with your own data. You probably have watched, I will not go into many details about that. You should watch a pre-course workshop that I did a couple of weeks ago. So in the course repo, there's this video and code that you can check where I talk more about LLMs and RAG and so on. So there in that workshop, what we did, we used Elasticsearch to index the data. I'll talk about the data a bit later. And then we used OpenAI to actually send this data that we retrieved with Elasticsearch to OpenAI and get back the response, so the answer to a user query. And I thought, like, since for RAG, search is such an important thing, maybe it's worth spending some time explaining the basics of search. So this is what we are going to do in this workshop. So we'll just implement a toy search engine. So it will not be a production-ready search engine. This is not something you should use in production. This is something just to understand the principles of how search works. And this will be an in-memory thing, like in memory index. So this is not something you can, like, let's say if you decide to run this and your machine goes down, then of course this will not remember the documents. So with that in mind, so let us start. I have already sent you the link, this build your own search engine repo. This is what we're going to use today. And the reason I have a different laptop, a different tablet with me, is because I can actually draw on this laptop. If you took any of the other courses we have on in DataTalksClub, maybe you remember this. So I have a pen and I use Microsoft Surface for drawing. And many of you asked what's the name of this tool that I use. It's called Drawboard. So I'm going to explain the basics of RAG. So as I said, RAG is retrieval augmented generation. And this R stands for retrieval, right? And this is basically search. R is search. The way RAG works is, let's say we have a user. And user has a question. Great. And actually, I forgot to talk about one thing, very important thing, the data set we use. So this is all here. So in our courses, we have a bunch of free courses, and these courses have FAQ documents, so frequently asked questions documents. And this is one of the documents for our data engineering course, free data engineering course. And it takes quite a while to actually load this document because the amount of frequently asked questions there is huge, like 300 pages or something like that, right? And we ask students to do, so before they ask questions about the course. So let's say they have problems with running Postgres and Docker, right? So what we ask them to do is before they ask questions in Slack, they go to this document and check like if there is already a solution, if there's this question is already there, because the problems students have are quite typical, quite common. Yeah, so they will 99% probability, with 99% probability, they will find answers here. But this document is simply pretty long. Like, yeah, so it says 200, almost 300 pages. It used to be, I think, more. It doesn't matter. Like, you can see that it's not super easy to find a solution there, but of course, like, this is what the students need to do. So what we're going to do today is build a system, or this is what we are going to do in the course. And today we will just implement the search functionality. Is we will use search to find things from this document, and in the course we will build a system for answering questions about the course based on the information from these documents. So this is what we're going to do in the course. So let's say we have a student, and a student has a question. I just joined the course. Is it late? I just found about the course. Is it too late to join? Right? This is a very typical question. And then instead of somebody replying to that, or student going through the FAQ document, we want to build a system that answers these questions based on the FAQ document that, yes, it's okay, you can still join. And the way this system works is we have a database with these questions. In the workshop before, we used Elasticsearch for that. And the way it works, we send this query to Elasticsearch. And remember, the query is like, I just discovered the course, is it too late to join? Right? We send it to the database, and then we get back, let's say, 5 most relevant documents. 5 documents, right? Then, well, we actually don't return to the user. We send it, let's say, here. And then what we do with this is we build a prompt based on that. And the prompt is something we send later to our LLM. So in our case, it was OpenAI, which we use ChatGPT 3.5 model, right? And then the model replies with the answer. And the prompt looks like that, can look like that. Question. Then we insert the query from the user, then context. So this is our documents, these 5 documents that we retrieved from our index, from our database, and then answer 1s. Right, so let me just make it cleaner. Okay, whatever. And then what LLM is doing is trying to complete the prompt. So it says, okay, so it stopped at answer. Let me answer this question, right? So this is how RAG works in simple terms. And as you see here, we have this database, this search engine. So this is such a crucial thing in any RAG system. That's why I thought that we should spend some time talking about that. And so here, search can be like, there are 2 types of search, at least for the purposes of this workshop. This is what we're going to cover. So one is text search, and another is a semantic or vector search. Semantic search. So text is like, let's say, again, if we talk about the query, I don't want to type, I don't want to draw it here, it's too long. Actually, I think I need to, like, I just discovered, there is a typo, whatever, the course. Can I still join? So this is the query. With full text search, we can find all the documents that have these words: discover, course, join, right? So usually in text search, at least without any extra modification, we're looking for exact matches. So a word is in the query, a word is in the document, and it's a match. We will see how to implement that. So this is a text search, right? Sometimes users might form questions that don't exactly look like documents in our database. So for example, let's say we have a question that looks like that. I just discovered the course, can I still join? So this is a document we have in our database. But the user says, I just found out about the program, can I still enroll, right? So all the important keywords, find out, program, enroll, they're kind of the same, right? So synonymically, semantically. So they're synonyms, so they have the same meaning, but they're different, right? So text search will not work in this case, at least without any heuristics. Plain text search will not work, but we still want to be able to discover these documents. And this is the case when we use semantic vector search. So in this case, we encode the query and the documents as vectors, and we use vector search for that. So this is something I will talk about in the second part of the workshop. So this is second part. And in the first part, we'll talk about this. We'll talk about text search. And now it's part 0, so I explained what we're going to cover. Right now, we're going to prepare the environment. And you actually don't have to do it the way I do this, because I'm going to use GitHub code spaces. You can use something else, like let's say if you have an environment already with Jupyter, Pandas, and scikit-learn, that's all you need to do. You can just start the environment, or start the Jupyter, and follow it from there. What I will do, and what you can do too, is use code spaces for that. So I'll call it search workshop, but you can call it any way you want. And I should be public. Let's add a README file, and we'll add gitignore for Python. I'm creating an empty repository, and there in this repository, I will create a code space. So maybe I was too fast. So here I clicked on code, and then you can either click on the plus, or create code space in main, and make sure that code spaces tab is selected, not local, not code spaces. And right now, what is happening is in the background, an instance of Visual Studio Code is created with some. So basically, there is a virtual machine, and this virtual machine has a lot of stuff there. So, for example, it has Docker. So let's say if we do Docker on hello world, it works. Yeah. What I'm going to do is I have Visual Studio Code Desktop, so I want to use it. And because we're going to we're going to use Jupyter, and for Jupyter we will need to forward a port. Yeah, okay. I have like a special tablet, that's why it's. I hope that I'll be able to continue using Visual Studio Code. Okay. So what is happening right now is I'm connecting to that code spaces, to that remote machine through. What's happening? I just tested it today. So, okay, let me think what I can do. So I was going to actually do some drawing. Maybe I need to use a different laptop. Trust me, it worked just a few hours ago when I was testing. And let me try one more time before I give up. Yeah, weird. Okay, let's improvise. So we'll use it. Yeah, apologies for that. Actually, let me see if there are questions. Yeah, I don't see any questions. Yeah, if you just joined, don't forget to like the video. And what I'm going to do is I'm going to connect to the same Zoom session from my other laptop, and then I'll just share my screen from there. It's the first time I'm doing this. I'm a bit nervous. Can you still hear me? I hope you can. Okay, so where did we stop? So I will share my screen soon. I will just open GitHub first and then share my screen. Okay, you can see it, right? So this is where we stopped. So this is the code space we just launched. And what I'm going to do now is click on Open in Visual Studio Code. I have already installed CodeSpaces extension. If you do not have it, before you can do what I show, is you need to go to extensions and then type CodeSpaces here, and then yeah, just install it. Probably it will also prompt you to install the extension. Okay, too bad I will not be able to draw, so that's what I was hoping to do with my tablet. But yeah, maybe next time. Right now, I'll just switch it off. If you don't have Visual Studio Code, then you can install it. I hope you can do that. And then I just open terminal by clicking Control tilde. And then here we have Python 3.10. And now let's install the libraries we need. Pip install. You can create a virtual environment if you want, but since we're in CodeSpaces, it's kind of like we're kind of in a virtual environment already. I mean, in a virtual machine. So what I'll install now is Jupyter. Then I'll install scikit-learn, and then I'll install pandas. For the second part of the workshop, we'll also need a few other libraries. But for now, let's just install these ones. And now to run Jupyter, I just do Jupyter Notebook. And yeah, it will just run the notebook. And we copy, go away. We copy this thing from here. And notice that we have an open port. So if we go to the ports tab, we see that the local port, the 8888 is forwarded to the remote port 8888 is forwarded to the local port 8888. And let us just, I pasted the link, I just copied. And of course, if for you the forwarded port is different, you will need to adjust the link. So let's just create a notebook. Yeah, select, make it a bit larger. And yeah, I'm going to toggle Where it is. So I want to, I don't see it here. Appearance. Like maybe it's a new version, so I wanted to hide this thing. I hope it doesn't bother you. Import pandas SPD. Just let me check that it works. Yeah, so it should be fine. This actually annoys me. So what I want to do is no, yeah, it's a new version, I guess. So I wanted to hide this bar bottom at the top. Anyways, let's see. So where is this the repo that we wanted to use? So this is the repo, build your own search engine. And I already talked about FAQ documents. We installed that, we opened Jupyter Notebook. And now I already showed you the FAQ documents, and we have parsed these documents and converted them to JSON. And this line of code goes to fetches that document with the request library, which I don't think I installed. Yeah, it's good that Codespaces already had the request library. So I should have also done, if you run this not on Codespaces, let me open a new terminal. So I should also have done pip install requests. Right? So this library for fetching, for making HTTP requests. And now this variable documents contains documents from these FAQ documents. So this is actually the question that we talked about. Can I still join the course after the start date? And the answer is yes, if you don't register, blah, blah, blah. So this is one of the entries in that FAQ. So what we want to do is we want to build a search engine that searches in this field, and in this field, right? And if there is a match, it shows us the document. And also there will be multiple matches. We also want to sort these documents by relevance. So the most relevant documents are first, and so on. And this way we retrieve, let's say, 5 most relevant documents. So this is how Lucene works. This is how Elasticsearch works. This is how roughly Google or Bing work too. Okay. And for that, let me check my notes. For that, we need, I will first convert it to pandas. So we can do this by doing pd data frame and then putting these dictionaries there, documents, right? And then we get this data frame. So you can see the document. And here I don't particularly like the order of columns. So it's first text section. So first I want to have column, then section, then question, and then text. Text is the answer. That's why, where it is, yeah. That's why I pass this extra argument, columns, which enforces the order, right? So if I specify the order of columns, then this will be the order. So course, section, question, text. And let's say we want to build a bot for answering questions about data engineering Zoomcamp. But we also have, if I look at the tail, we also have other courses like ML Zoomcamp and MLOps Zoomcamp, which might have different answers for the same questions. So we first want to limit our search space to only a particular course. And with pandas, it's pretty easy to do. So if you know pandas, yeah, for some reasons autocomplete doesn't work for me too. Live demos. Zoomcamp. So typically for pandas, the way we do it is we do filtering, right? So if we have a data frame and we want to have a sub set of this data frame, right? So we use this syntax. So we filter by this field course and we select only entities from here, right? Only questions about the course. Right? So this is how we can easily limit the answers to the course only. And now we will start with the interesting part, is actually implementing the text search. And for that, we will use scikit-learn. And right now, it would have been very nice to have my tablet because I wanted to illustrate something. Let me improvise, right? So in order to do that, we use a thing called vector spaces. So let me just, I'll write it here, vector spaces. So a vector space, and this is true for like search from 70s to search nowadays, is we take a document that we have. The document is, can I still join the course after the start date? And we turn this document into a vector. Turn the doc into vectors. The way we turn them, it could be different, but the easiest, so for text search, the way we can encode it is, let's say we have a matrix with many different columns, and for each column, for each word we have in our dictionary. So we have a column, and each document is a row. So this is called term document or document term matrix. Let's call it term document matrix. We have rows, documents, and columns are words or tokens from this. So in our case, let's say if we consider only words like join, course, start, and date, we will have a column join, where for this document we will have one. For the column course, we will have one, and for the column start, we will have one, and for date, we will have one, right? And in scikit-learn, we have a class, a transformer that is doing exactly that. It's called count vectorizer, and it's in scikit-learn, I think pre-processing. Well, let me just copy it because I don't remember the exact library. So this is the place where it lives, right? So scikit-learn feature extraction text count vectorizer. So count vectorizer is a vectorizer, and vectorizer is a term that we use for turning texts into vectors, right? So this is, we have these vector spaces, so we are interested in turning our documents into vectors, and a vectorizer, this particular count vectorizer is doing exactly that. So let's initialize it. Right? So we create a count vectorizer, and then we, in terms of scikit-learn, we feed it, we train it. So what we are doing here is we look at what words in this in our data set exist, right? So we do fit, and let's say first we want to do it for text, right? So it will be a vectorizer for the text field. Right? So we have count vectorizer, and then we will. Oh, actually, I have this get features names out. We can see all the different terms or tokens or words we have in our document. And there's quite a lot of noise, actually. Like every single token in this document is turned into this matrix, into this column of a matrix. And if we look at, yeah, so there are 6,711 distinct tokens in this dataset, which is pretty, like, quite a lot. And most of these tokens, terms, they just use in one document and not in others. So for that, we can say that, let's say we only care about the documents, the terms that appear in at least, let's say, 5 documents, right? And then the column names, these terms set is much more meaningful, and we can see that it's much smaller, right? So we focus only on important words that appear in at least a few documents. We don't want to look at all the documents. And here I have an example which we should probably start using. So here it will be easier for us to see how exactly this count vectorizer turns text into vectors. So let me just do it one more time. I will remove this pin df. df stands for document frequency. So I will fit it on these documents. I think, yeah, it's kind of conflict documents. Document, let me call it doc examples. And I will execute this line again. So now we shouldn't overwrite it. And then if I look at get features out, so these are all the different terms we have in our documents. And now we can transform these documents into a matrix. So in doc examples, that's the name, right? And let us call this matrix X. So this is a matrix. It's a sparse matrix, meaning that for all the zeros, we only care about non-zero entries. So we will not go into like details of what dense or sparse matrix is, but we can see what exactly is inside this matrix by invoking toDense. So we can see that this is the first document. So the first document contains these tokens 15th, 2024. It doesn't have the word on after, it doesn't have the word and, it has this word and so on. So we can, what we can do is we can create a data frame for that, just for us to be able to see what's actually inside. So create a data frame like that. And then, of course, we want to know like what kind of words are here. We can say columns is this. So now we can see what exactly is in each document by doing something like that. And of course, we can transpose it. So then for us, it's easier. So this is document number 0, 1, and so on. And these are the terms, right? So we see that. So usually our matrices are not transposed. This is just visually is easier to see. So we can see that, for example, document number with ID 4 contains the word and yeah, Python is also is only in the last one. Yeah. Right. And then we see things like and, for, not on. So they're not super relevant. So these words are called stop words, and we can remove them. We can disregard them by saying stop words English, right? So then count vectorizers, like these vectorizers, have stop words for many languages, or maybe just English, I don't remember, but at least for English it has. So when we do that, we see that it removed some of the words, and then yeah, so now it looks differently. So we removed some of these words we're not interested in, right? And yeah, so this is how it works. So this representation is called bag of words. So let me add a note here. Bag of words. So what is interesting in this representation is we don't care about word order. So we just care about the presence of the word. So we know that this document and this document have the word course, but we don't know exactly in which order this appears. It's at the beginning, at the end, in the middle. So in this representation, we lose this information. So word order is lost. And typically we use sparse matrices for that, for the representation, because we have most of the records are 0, right? If we think about, remember in the previous example, we had 6,000 or 7,000 words, Of course, most documents don't contain that many words, so we will just have one, like maybe in our case 10 ones, right? And the rest will be zeros. That's why we use sparse matrices. And yeah, so this is how we use count vectorizers. So then we talked about term document matrices, back of words. And then one other thing I wanted to talk about is TF-IDF. So let me just do this real quick. So I will check what I implemented here. So this is so I will do this for documents text. And remember, we also added here minimal document frequency 5, right? So we have this, like maybe we shouldn't transpose it. So we have 900 documents, and these are the words that are there, right? So I will remove this. This is not interesting for us, but this is something we will start with. So we talked about what back of words is. And now, yeah, maybe I should also mention that. So let's say we have the word yes, right? So maybe yes contains in many documents, and it's less important than the word YAML, because the word YAML contains only in a few documents, right? So here the logic is the more frequent the term is, the less important the term is, right? So if I look in my query, I type YAML, then the words, the documents that contain the word YAML are more important, because YAML is a very infrequent word compared to some other, right? So for example, the word yes, or YouTube, or I don't know, ZoomCamp. Maybe ZoomCamp is a very frequent term in our dataset, right? So this way, it gives us, so we kind of can understand which terms are more important, which are less important. And for that, we use TF-IDF vectorizer. So TF-IDF is a way to give more importance to less frequent terms and more importance to less frequent terms, right? And the only thing we need to do is replace count vectorizer with TF-IDF vectorizer. The rest stays the same, and we will now see if I round it to 2, that instead of ones and zeros, we have, like you see, for example, 0.15 or 0.21, because 21, so this 6 appears more often than 9. So that's why it's considered the more important, right? Or the word, do we have like normal names? No, whatever. Yeah. So like words like YAML will have more a higher score than words like yes. Actually, these are the documents, right? And these are the words. I should remove this transposition. And then, so the word yes is this one. Yeah, funny thing, in this data set, maybe the word yes is less frequently used than YAML because it has more importance, or maybe it just appears multiple times. But you get the idea. So this is what we're going to use for scoring. So we'll use this TF-IDF vectorizer. So we turn a word, we turn a document in vectors. And now each term in this set of documents has different weights, right? So the more important the word is, the higher the weight for this term. Okay.
So this is an example. Let me actually try to copy it and see. Yeah, I think I'm applying it to this one, right? Yeah, I think this is what I wanted to show you. And now we need to do the same thing. So this X is our matrix, document term matrix. And now we have a query from the user. Let me just, instead of typing, copy it. So do I need to know Python to sign up for the January course, right? So what we do is we apply our vectorizer to turn this query into a document. And this is how this document looks like. Yeah, it's actually like most of the entries are 0, but some of them are non-zero. And maybe we can actually see which of them are non-zero. So we can do it like this. So what we are going to do is, so names is, remember, is the list of columns, a list of terms. So here we will now get these arrays with names. We will kind of connect them. Let me just show it to you. So first we'll see the query. I think this is not something I intended to show, but let's just go with this. Yeah, go away. So we see all the terms, and I hope there will be one somewhere. Yeah, so, okay. So this is the course. You see? So most of them are 0, but sometimes they are non-zero, and these are the terms from our query. And the same is for the documents. Like, for example, if we take this second document, I remember the one about if you can still join for the course. So then I think for the word course, if I will be able to find it, we will probably have something like non-zero 2. But I guess you'll have to believe me, I am not able to find it easily, right? And then in this case, we can see that, okay, for the word course, in both cases, we have non-zeros. And then I see recommendation apply filter. Yeah, I can do that, but like I'll spend more time figuring out how to do this now than just talking about this. Even if you follow this tutorial along, you can also apply filter. Actually, I was supposed to show this with this example, but yeah, I hope you're still not lost. Okay, so now the idea is that if a document and a term contain the same words, they're relevant. So the document is relevant to the query. And because each of these terms is weighted, because we have this TF-IDF weight, we now know which documents are more important for this query. And then what we can do is we can just rank our documents according to this criteria. So what we can do is we can multiply the weight of the course in the query with the weight for the course in the document and sum across all the matching terms, right? This will give us a measure of similarity, how similar the query is for the document. And if we do this for all the documents, then we can score all the documents, and then we can simply rank the documents by the relevant score. And let us just implement that. Right? So this, what I just told you, this multiplying and summing is called dot product. So if you have ever taken a linear algebra course, this is exactly that. So in linear algebra, we have a matrix, and we multiply a matrix with a vector, and this is how we can compute this easily. So we are going to implement that. I will just do x dot. So this will compute the similarity score. And I think I need to transpose it. Right. So right now you might feel lost because like I started talking about dot product and matrix multiplication and like all that. Don't worry. So here this is a way for computing the similarity between a document and a vector. And we can do this for every document in our dataset very quickly because this dot product, this function is super fast. Like this is very, very fast. Right, and then if I do to dense, we can see that this is the result for the first document, this is the similarity for like fourth document, and so on, right? So now we can compute the similarity for all the documents, right? And this with so let me think how to formulate it. So I see a question: what kind of similarity is this? So this is actually cosine similarity. So the way we compute cosine similarity is we use this multiplication and then do some normalization. But like for the purposes of this workshop, we can just say that in this particular case, this is cosine similarity. And I don't want, again, to go into details of how exactly cosine similarity is implemented. The idea is that it gives us a number that is doing what I described here previously, that says how relevant this document is to the query. And I will just now import cosine similarity. Yeah, where it is. Okay. I think it's from scikit-learn. Where is autocomplete? Cosine similarities scikit-learn. So it lives in matrix pairwise cosine similarity. So this is what we need to import from scikit-learn matrix pairwise import cosine similarity. And we do it this way: cosine similarity between our matrix X and query Q. Right, and then it gives us the same result, right? So it gives us this measure of similarity between each document and the query. Now we can turn it into a vector like that. So it was a two-dimensional matrix with one column. Now it's just a NumPy array with one dimension. Right? And this, for each document, it gives us the relevant score. So let's call it score. And now what we need to do is we can sort this. And when we sort, we pick the documents with the highest scores, right? And I'll use NumPy arc sort. So here, when we sort, of course I need to import NumPy as NumPy. So what it gives us is, instead of giving us the actual values, it gives us the indices of the document. So the document with this index has the highest score, the document with this index has the second highest score, and so on. The thing is, it sorts, so in our case, the lowest record is 0, the highest record is, I don't know, something. So this actually has 0 score, and this is what we are interested in. So this top 5. So what we can do is just take from -5 to these documents. Yeah, I think I did it correctly. Let us check. I log. Maybe I should use a different query. So let me use the query from the example I gave previously. I just discovered the course. Is it too late to join? Right, and then let's see. So the document number 22 text is the highest matching document. Well, I guess It matches the word course. Let's see the other one. Here's how you join Slack. Or yeah, so this one is one of the relevant ones. Right? Yes, you can. You won't be able to submit some of the homeworks, but you can still take part of the course, right? So this way we find relevant documents. And yeah, because not all of them are super relevant. So some of them just match the words, but not necessarily give us the answer, but one of them actually is relevant. Okay. And we can do this for all the fields. So we have field section, we have field question, and we have field text. So let's just let's implement a search across all the fields. So I think I'm looking at the time now, and it feels like it'll take more time than I expected, but it's fine. Like if you don't have time now, you can leave now and then come back later, because the recording will stay here. And yeah, you can just come back and later watch it. So now what I want to do is to go across all the fields and pick a count vectorizer to that field. And this is something we can use for search. So let's call it. So we will need matrices, and let's let it be a dictionary. And then we also need vectorizers, right? So matrices are these X's, and vectorizers are these CVs. And then, yeah, so first we create a vectorizer, we feed it. So then we have the X, which goes to matrices, X, and then to vectorizers, CV goes to vectorizers, CV. Okay, so now it was rather fast, suspiciously fast. Let's see what we have in matrices. Yeah, we have all of them, right? So of course, text is the answer. It has most of the information. So it has more token than others. Then question has second largest amount of tokens, and then section is usually a small, like it's just, do we have it here? So section is just to which section this question belongs, right? So yeah, now we have matrices and vectorizers for all the fields, and now we can look across all fields, right? So let's say our query is, let me copy it one more time. I just discovered the course, it's too late to join. So we can score it across all the fields. So for example, first we'll create an array with all zeros, and then we will loop over all the fields, and for each field we will compute the similarity, and then we will sum similarities across all the fields. So the size of the matrix will be the size of our data frame. So we have 948 documents. So we'll create a NumPy array with just zeros of that size, and now for each document we'll compute the similarity. So it's again for field and fields. We'll do it for all the fields. We get first we need to get a vectorizer. Then we do fit transform of this query. We get back this vector Q. So this representation of this query for this particular field. Then our X is matrices field. We compute cosine similarity between X and Q, right? And then we flatten it to turn it into a vector. So to one-dimensional array instead of two-dimensional matrix. So let's call it F score, right? So similarity for this particular field. And then the total score will be score plus this score for this particular field, right? And then I have a typo fit transform, right? And then another typo. Yeah, of course, I just need to call transform. Apologies. We already fitted previously. Now we just need to do transform. And I just need to execute it one more time, I guess. Yeah. So now the score is there. We just do it one more time. So I'll call this variable IDX, short for index, and then data frame iloc IDX will give us all the vectors, all the documents with answers. Right? Yeah, and then we already see a problem, right? So the problem is, let's say we want to build a system that answers questions about data engineering Zoom camp. But here we have answers from other courses. We need to add filtering. And let us do that. So we can say that our filter, what filters, so we can have multiple filters. Let's say in our particular case, we'll just have one filter for course, but let's say if we have a different data set, could be course and so, like even for this one, could be course and section, right? Or if we have a different data set where we want to filter across two fields, this is how we can do it. So add data engineering Zoom camp. So basically right now is what we do is we do post-processing. So we only keep the results that are interesting for us. And the way we do it is for field value in filters values is what we do is something we did at the very beginning. So we did, do I still have it? Yeah, remember I showed you how to filter documents only for particular course. So this is what we are going to do now. So let's call it mask. And for mask will be that this field equals to value, right? And then this is a Boolean mask. So if this is true, then the value is true. And if this is false, false, so this is not data engineering Zoom camp, but ML ops Zoom camp, it will be true. So we can turn this into as type int. So now let me just show you how it looks like. What? Items. Yeah. Yeah. So we see that this is the mask. And we can turn it into, so this is a pandas series, right? Where one is when it's true, 0 otherwise, and when we write values, we get an NumPy array. Right? And then what we can do is we can multiply the score by the mask. And if it's 1, the score stays as is. If it's 0, it becomes 0, right? So this is our score at the end. Now we have a lot more 0 records at the end, right? So when it does not match. And now this is something we can, again, sort and show. So here, in this case, we have only answers from the data engineering Zoom camp. And I think one of them is, yeah, kind of all the course after it finishes, when the course starts. What can I do before the course starts? Yeah. So actually, I don't think it contains the answer to this query, but let's say it's 10. Yeah. Probably it's somewhere here. Right. One more thing that we can do is the question field is, at least it feels more important than the text field, right? So when I ask a question and if a term in the question field matches one of the terms in the query, it makes this document more relevant than if the answer matches, right? So we can give more boost, more score to question rather than text. And this is how we do it in Elasticsearch. So in Elasticsearch, there is a concept of boosting. So we give more importance to more important fields, right? So let's call boosts. We can call it boosts. And for example, the question field will have more importance. So let's say it will be 3 times more important than other fields. And then what we can do is get the boost from here, from this dictionary. And if it's not there, the default one will be 0. And then we can just multiply our score by this. So this effectively will give more score to the score from the question field rather than to the others. And then let's say if we want to give text less importance, we can also do that. So then text will have only 0.5 boost, which is like less than 1. Then section will have 1 and question will have 3. I will just try it with question now. And then let's see what we have. So the course starts. So now, yeah. Actually, it still doesn't look like what I wanted to see. So what I did before is, maybe I don't do the sorting right. So what I did before is instead of doing it this way, I sorted the negative of the score. So meaning on the most important come first and then the rest, and then take top 5 from here. Let's see if this improves the situation. Yeah, that's actually the same results, right? It doesn't change anything. Wondering why, but yeah, I guess this is just how I formulated the query. So I think these both ways of getting the most relevant questions are the same. So this is how we perform search across multiple fields, and we also add filtering. And this is exactly the functionality we use in the workshop we already did from Elasticsearch. So in Elasticsearch, we filtered by the course field, and then also gave more boost to the question field, and then used section and text with no boosting. So now we can actually put this together in one class. I will not type it right now. What I'm going to do is I will just copy this document. So this is everything we implemented, but in one class. So what we do is here, fit part is we go across all the fields and fit transformers and save matrices and vectorizers. And in search, we do basically what we did here. So first we compute the cosine similarity, we compute the boost score, and then we do filtering, and then we do keep the top results, and then return the results. So now let's just use this class. I will again skip typing. I will just show how to use it. So first we create an instance of this class, text search. We say that these are the text fields that we want to, we can say index. What it actually means is we hit count vectorizer on them, right? And then perform search. And then this is how we specify boosting, this is how we specify filter, and this is how we specify query and the number of results we have. And we get back the answers. So, and it's already in the same way as Elasticsearch returns. So it returns you the dictionaries, not like lines of a data frame. So this is something that we might actually use in the course, and we already put it. I created a small library called MinSearch, which is doing exactly that. So this is everything we talked about today right now is put together in a single Python file, right? Yeah. So this is something you can use. This, I believe, is a good illustration of how text search works. And remember that this is an in-memory implementation, so all these matrices and vectorizers are kept in memory. Yeah, and this is not for production, it's just for illustrating how text search works. And I also told you about two types of searches, the text search and vector search. Most of the time we spend talking about text search. We still have a bit of time. Probably it will take longer than I expected. Now we'll take about vector search. And vector search is useful when the words don't match exactly. And I will show you a few things. They're pretty old. So the first thing I will show you is applying singular value decomposition. This is a scary looking word, scary sounding word. But this is just a way of reducing the dimensionality of a matrix. So let's say we have this matrix, and the dimensionality of this matrix is it has 1,333 columns, right? We can reduce this dimensionality. We can compress the matrix to, let's say, only 16 values, right? And singular value decomposition is doing this and trying to preserve as much information as possible from the original matrix. And I have actually a good illustration here. So this illustration is for images, not for text, but in text it's very similar, right? So here in this example is, so they took this picture and applied singular value decomposition and only retained the first, in this case, 5 vectors that come from SVD, right? And you see it already kind of resembles the original image, right? And then the more columns you use, the more dimensionality you have, the more similarities. It's kind of similar maybe to, well, it's not exactly JPEG compression, but you can think about that. So it's a lossy compression. So the picture is not exactly the same as the original one, but it tries to retain as much information as possible while compressing the dimensionality of vectors, right? And it works with images, and it also works with text. And I think there is a very old paper called Latent Semantic Analysis from the 90s, which talks about doing that. Yeah, so I have it's in German for some reasons, but yeah, so you see that if you understand German, oh, yeah, it was first published in 1990. So it's a pretty old. So these things have been around for some time, and I will now show you what exactly is happening when we do this. So I'll just copy this as we don't have a lot of time, so we'll save some time typing. So we will now apply SVD, so this singular value decomposition, to the text matrix, right? And then, so let me just do it step by step. So now our X, did I call it? I don't remember. Vectorizers. Yeah. So our CV is the text vectorizer, the vectorizer for text, and X is the matrix for text. So now we will do fit transform on X. So which means that we will reduce the dimensionality of the X matrix, and we will, if we look at the shape now, it will have only 16 columns. So the same number of rows, but only 16 columns. And this is how the first document looks like. So you see now, instead of like a ton of zeros and a bunch of non-zero records, we have a dense representation. So this representation of a document is called embedding. So it's a dense representation of the document, so when we reduce the dimensionality, SVD tries to capture as much of the original information from the original documents as possible. And what happens then is doing that synonyms such as like enroll and sign up and whatever, they're kind of reduced into the same concept, let's say, right? And similar words kind of grouped. So this way of turning documents in dense vectors captures these semantic similarities between different words, right? And then at the end, we get this representation where we can think of this as some sort of core, to what extent this document belongs to a certain topic, right? Let's say the topic of enrolling to the course, or the topic of Docker or whatever, right? And we can do the same thing with the query. So I'll just copy again the document, like the code. So we do the same with query, right? So I take the query from the user, I apply the same transformation as we did previously. So this creates a sparse matrix from this TF-IDF vectorizer. And then we use SVD, singular value decomposition, to turn this representation into a dense vector. And this is what we have, right? So we can represent documents from our database this way, and we can represent the query in the same way. So now what we do is again computing the cosine similarity. So here the principles are the same, except the representation of a document is different. So previously we had these sparse matrices, now we have dense small matrices, but the principle is still the same. Now we simply compute the cosine similarity, the similarity between the entire database that we have and the query, right? It gives us a score, a relevant score, and we can use this score for ranking the documents. And this is, let's just see it for illustration. So we compute the similarity between this vector and this vector, and this is it, right? And we can do it across all the documents like that. So we take the entire X, we take the this representation for the query, then we turn it into a one-dimensional array, then we sort it by relevance, and then we see the answers, right? So the answers, what we can find, I think it's more or less similar. So, and actually, like, as you see, if I show you maybe this one. So now, okay. So this is, we don't do any filtering here. I was going to say, you see, like the relevant answer is the first one, but yeah, this is for a wrong course, for a different course. Well, at least if this system we used it for machine learning Zoom camp, like the most relevant result would be the first one. Can I hold the course? Can I? Yeah. So the answers are still relevant, and also this search is actually to some extent faster. Well, not always, but like there are some benefits for this, right? First of all, we take care of synonyms. Then, this is probably the major one, right? And then we also have these vectors that we can use for other things. Like, for example, let's say we want to train a machine learning model, and we just can put this into our XGBoost or whatever, right? With the sparse vector, the original one, it would be much more difficult to do this. So this is how we use SVD, singular value decomposition, for tuning documents in vectors. There is a bit of an issue. It's maybe not an issue, but more like something to consider. Like if we think about if we try to interpret these terms as the extent to which it belongs to a certain topic. Let's say the topic is Docker, and the score indicates how relevant it is for the topic Docker. Then it's kind of very hard to interpret negative values. Like, what does it mean it belongs to like a certain topic with minus 0.08 score, whatever, right? Now, we of course don't know the topics, so the topics are unknown to us. We can of course look at the documents with high score in this particular dimension and see that, but this is some internal representation. We don't really know that. But still, like in the X matrix, we have only positive values, but somehow here in SVD we have negative values, and they might not be easiest to interpret, right? So there is a different way of compressing this matrix, and it's called non-negative matrix factorization. And the idea there is that if the input is non-negative, the output will also be non-negative. And I will just copy this. So it's the same thing. It's just instead of using SCD, we use non-negative matrix factorization, and I forgot to add the imports. Non-negative matrix factorization. Yeah, it's decomposition NF. Scikit-learn, decomposition, import NMF. And right now we see that we can do the same thing. And this is how documents look like. And also as a bonus, we have a lot of zero records, which is a good thing. So we can see that there are two topics to which this document belongs to. To this document, it belongs with this score, and to this document, it belongs with this score. So probably this document is about this particular topic. So we can think about this as topic modeling. So we have 16 different topics or concepts, and this document is about this topic, like 1, 2, 3, 4, 5, 6, 7th topic, and 9th topic, and these are the scores for these topics. Right. I'll check the questions you have soon. Let me just finish that. So we do the same thing now with the question, right? So we see that this particular query we have belongs to this topic, this topic, and this topic, but not really to this topic. So yeah, they have some intersection between this and this, right? So now we again compute this cosine similarity. Let me just copy this thing. We compute the cosine similarity, and again we get that, right? So, and this is actually quite good, right? So this is what I wanted to see, right? Yes, even if you don't register, you're still, yeah. So like even if we don't use here question at all, we just use text, we can find the answer, which is pretty good. So this is how, like, this is the simplest possible way of creating embeddings, and these methods of creating embeddings have been around for very long. Like this latent semantic analysis, which uses SVD, is like as almost old as me, right? So it's been around for quite some time. The issue with these things is that the input, the source it uses is bag of words, and in bag of words, we'll lose the information about the word order, right? And sometimes the word order is quite important, right? There are applications where it is important. For RAC, I think it might not be that important, especially for this particular data set. But for some cases, it might be important, especially for maybe more advanced RAC uses where queries are quite large, maybe. I don't know. But sometimes you might actually care about the word order. And yeah, before I start the next topic, so I wanted to talk about BERT and creating embeddings with BERT. Let me quickly take a look at the questions. Compressed embeddings from 3D help with that, with memory usage. So I think I answered that. So they capture the semantic similarity. Do we need to transform X matrix and query vector with the same transformer? Yes, exactly. So like if we use, so remember how we did it here for this class, right? So we, for each query or for each field, we had its own countercharacterizer, its own matrix. And if we wanted to add, let's say, singular value decomposition or non-negative matrix factorization, then of course each of these fields should have its own SVT or NMF instance, right? So we can maybe have self embedders. I don't know if this is the proper word, but this is something that turns like high dimensionality vectors and low dimensionality vectors. Let's call them embedders. And then we would need to also say SVD, blah, 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 fit transform. And then actually matrices here, if we want to ditch text search completely, then matrices would be like X embedding after we embed. So here we do fit transform, and then X embedding would go to matrices. Here, right, and embedders would have SVD, right, or NMF or whatever. Yeah. Let me check if there are other questions. We can try to choose number of topics. Yeah, like this is a different topic, maybe not for today. But of course, there are so many parameters now, like you can choose different ways of compressing your matrix, different dimensionality. So you need to have a way to numerically quantify the quality of the results. And typically in practice, we use methods like, we use things like mean average precision or precision at 5 or things like this. So these are the metrics we use for measuring the performance of informational retrieval systems. And there is a very good book. It's called Introduction to Informational Retrieval. It's free. You can download it here, PDF. And they should talk about this relevance feedback. But like in general, most of the topics we talked about today, like for example, this matrix decomposition, latent semantic indexing, they are covered there, right? I don't see though. I think they talk about things like precision recall and different other metrics. Yeah, but metrics, you can Google metrics for ranking. And then you will find like in DCG, mean average precision, yeah, precision at K, recall at K, like maybe, yeah, this is something that you can check. This in DCG is quite commonly used. And then you can use that as a guide to selecting like which embedder you should use, well, how many dimensions you need to choose, and so on. Okay, maybe I'll quickly show you how to get embeddings with BERT. We will not spend much time here. I'll just show you how to get started, and then this is something you can do after the workshop. We'll not spend a lot of time here. So what do we want to install for BERT? So BERT is a neural network that turns, maybe you have seen this, it's called BERT. It's bidirectional coded representation from transformers. Yeah, so it's a mouthful, but basically this is a neural network that turns like a document into an embedding, right? So this is what we need. And these embeddings, they capture not only semantic similarity, but also word order. And this is especially useful for things like find out more, or like this longer phrasal verbs or whatever. Or when we have negations, like don't do this, and things like that. Yeah, so what we do we actually need to install? Yeah, just transformers. So transformers is a library from Hugging Face. Hugging Face is, so this is how to say, like a repository with models. So there are different models. So they have this repository, a database with models, and everyone can just access these models and use them. And we will use Hugging Face a lot in the course too, because they host a lot of LLMs there, but also they host like a lot of neural networks, for example, BERT. And yeah, so we install that, transformers and TQDM. TQDM is just like a progress bar. And while it's installing, I will copy this piece of code. So what this piece of code is doing is, these transformers usually have libraries that are models that are implemented in PyTorch. And you can take the model, for example, BERT based on cased. It's already trained. All you need to do is just download it from Hugging Face and then use it, right? Then let's execute that. And Torch, we will, because they use Torch, we will need to use it in one case too. So now we download the model. It's a rather small model compared to what we are going to deal with in the LLM course. But let's see how we can use it. So there are two things we download: the model and the tokenizer. So tokenizer is something that turns texts into some representation. Let me just show you. I think it's easier. So first we have two texts. Yes, we keep the materials after the course finish. So what it's doing is it turns the text into this, right? So this is probably some indexes. For example, the word yes. I actually don't know what exactly, but this is some representation that the neural network expects. So first we turn our document, our text in this representation, and then we feed it to the neural network. So this is how we actually do this. So that's why I need to import Torch here, because supposedly it helps to make it faster. So we feed this input, this stuff into the model, and this variable will contain embeddings. So let's see what we have. And I will just look at the shape first. So now, yeah, so there are two documents, and then it creates two matrices for these documents, right? So this is kind of, oops, multi-dimensional. So for each document, we have a matrix. This is not super convenient. So what in practice we do is we just take, like, let's say, what's the shape of this? So 15 and 700. So what we do is we sum across, or take the average value across the rows, right? And then this is something we use as an embedding. And this is the code for doing that. So we simply take average or sum across the rows. And now we have this, right? So now This is an embedding for the document number 1. This is an embedding for the document number 2. And yeah, well, we have negative values, but like in BERT, yeah, if we don't think about topic modeling, like we don't really care whether the values are positive or negative. And supposedly it works better, but again, the dimensionality is quite high. So for datasets like we have here, this is actually an overkill, right? Because like look at our X. Like even the sparse matrix is just a little bit, yeah, bigger than that. So BERT for this particular example would be an overkill, but it's much more powerful. Like for more complex documents, for more complex queries, it will perform better. And of course, now we need to compute it for all the documents, for all the fields. So we can compute it for the field section, for the field question, for the field text. And then we follow the same approach as previously, right? So we just take our query, tokenize the query, and then extract the embedding from this. This is how we do it. You can go through this code. I don't think it makes sense to go through this now. So if you're interested in that, just go through the rest of the tutorial. And there was one more thing I wanted to discuss. We don't have time today a lot for that, is practical implementation aspects and tools. Because here, right now, what we discussed, what we did is a toy example. This is not something you use in production. This is just illustrates the main principles of how search works, right? So how relevance search works. So that the main idea that we represent all the documents and the query in a vector space. It could be a back-of-word space, it could be a BERT space, it can be embeddings from LLM, whatever, some sort of vector, right? So vector is nothing else but a one-dimensional NumPy array, right? And then we compute the similarity between all the documents that we have in our index and the query, right? And this is the main principle of relevance search. And in this particular example, we had less than 1,000 documents. So we can of course afford computing the similarity between the query and all the documents. It's simple, it's very fast. But let's say you're Google and you index the entire internet. Like you cannot, like when I type latent semantic analysis, you cannot go over all the documents on the entire internet and compute the similarity between that. Of course, you need to do something faster. And there are two key concepts, two key ideas for that. For text search, we use a posting list in information retrieval or inverted index. It's called inverted index. And then in this inverted index, there is this posting list. This is something that Lucene uses in order to quickly retrieve documents. So if you're interested in how this is implemented in practice, how text search, fast text search, that you can index like millions and millions and millions of documents and it still works fast. So these are the key ideas: inverted index and posting list information. What did I say? Yeah. So these are posting list. Yeah, there is even video like how exactly it's implemented. And then another idea is for vector search is LSH. LSH is latent semantic hashing, locality sensitive hashing, sorry. And a very good implementation that is pretty fast and works quite well is a random projection, right? And actually, random projection, I think there is a random projection in scikit-learn. So the idea here is that we take this long embedding and turn it into a bit vector with ones and zeros only, right? And then when it's in this form, we can still compute the cosine similarity between the bit vectors. And it is roughly the same as the cosine similarity between the regional vectors, right? So it gives us a very powerful and fast way of computing similarity. And also there is a way to make it faster. But yeah, I don't have time to explain it. So maybe you can, like there is a thing called LSH binning. This is exactly how it is usually implemented in different vector databases. So they use LSH, they use binning for quick retrieval. For example, min hash, or yeah. So there are different. If you check locality sensitive hashing, you will find a lot of interesting things about that. So this is how it's implemented in practice in vector databases. And there is a good course about that. I think the course is pretty old, like 10 years old. It's called Mining Large Datasets or something like this, or Massive Datasets. Massive Datasets. Mining of Massive Datasets, yeah. So this book has a chapter about, you can guess that it's rather old book. So they have a chapter about LSH. Yeah, this finding similar items and LSH. So they talk how this is actually implemented in practice. Oh, yeah, so I managed to cover most of it, I guess, not with the speed I wanted. I also wanted to talk a little bit more about how to implement like the main ideas behind LSH and random projection, but this will be like home reading for you if you want to learn more about that. Let me go through the questions and then we'll call it a day. Could a specific eigenface embedding do better than SVD? Yes, or maybe not. Like the only way to find out is to come up with some sort of evaluation metric that is important for you. We talked about them like NDCG or precision at 5 or recall at 5, whatever. And then you evaluate different embeddings and look at this course, look at the metrics. And the one with the highest metric, the metric you care about, is best. Right. You should also look at the speed, of course, like if we talk about using BERT, then of course it's a heavy model. Then we need to spend more computing resources on computing these embeddings. And if simple SVD gives almost the same metric, almost the same precision, but just a little bit worse, then maybe this small incremental change in the metric is not worth spending a lot of money on these BERT vectors. Okay. Do this method struggle when the user query contains words that don't appear anywhere in the FAQ document? What I showed you, yes, because we feed the count vectorizer. And if we don't see the word anywhere in the document, then the count vectorizer does not know about this word at all. Like it doesn't know that it exists. And when we try to do the match, then yeah, we will not be able to match with these documents. BERT, on the other hand, is trained on very large databases of text. So it knows probably about all the words, right? So then in case of BERT, which could be like one of the advantages, or other transformer models, not necessarily BERT, with them we will still be able to match documents, even if the term in the query does not exist in our database. Is there a way we can update the TF-ID of matrix so I don't have to append the new text doc to the original dataset? Yeah, I mean, you can just do, instead of doing fit transform, you can just do transform and append it to the matrix, right? One. way of doing that. Of course, this is something we did not talk about in this workshop, is how do we index more documents, right? So we assumed here that the database we have does not change, which in reality is not necessarily true, right? And again, this back to the point that this is just a third example to show how relevance search works, but there are many, many aspects we didn't talk about. One of them is indexing new documents, for example. And for that, you should use something like Elasticsearch. They can just handle this easily. Do we still have the curse of dimensionality working with that product? Not in this particular case, no. Yeah, too many new concepts. I agree. Yeah. I think I was lost myself a bit during the presentation, and if I was lost, maybe you also felt like, okay, what's happening? Maybe if you go over this again, follow the tutorial, also implement it, and also try to follow this, because I deviated a little bit from the document. If you just follow it, maybe it will be easier for you. Yeah. And then also, like, there is a notebook that you can just use. The notebook. So this is the notebook I used for preparing for the workshop, and you can just follow through this notebook. I think I forgot to update the README. I think if you just follow this through this notebook as I speak, then like if you have the workshop and this notebook, hopefully some things will have more sense, will make more sense. But yeah, it takes time, right? So my master thesis was about information retrieval, about search. So I've been around these things for quite some time. And yeah, I still feel lost, like especially with all these new things like embeddings, I mean like this BERT embeddings, LLMs. Yeah, it's a lot of information. So if you want to understand this, go over the tutorial one more time, check this notebook. Also, the resources I shared will help. Yeah. Well, I don't see other questions. I guess most of you already left, and those who did not, enjoy the rest of your day. And if you're in Singapore and still watching, have a good night. Yeah, I guess that's all for today. So I hope you enjoyed it. And if you want to follow this tutorial and find some discrepancies, because like I also a bit struggled today, because like an import was missing or something like that, I'll appreciate pull requests. So that's all for today, and to see you soon on the course. And remember, it starts in less than a month, so sign up. And this is something we will use in the course directly or indirectly. And the class I implemented, I showed you, we actually probably will use in module 2. Okay, don't forget to like the video, sign up for the course, send